Hello, I'm Tim McClanahan, the Director of Science for the Wildlife Conservation Society. Today I'm going to be presenting efforts to understand sustainable nearshore fisheries in the tropics. I'll be specifically talking about our East African situation, a lot of detail about the fringing reefs of Kenya, but in the end I'll compare fringing reefs with island reefs in Tanzania. We've been collecting data in many Kenyan reefs since 1995, making regular measurements on landed catch in different categories. We've been collecting prices along with that data, and the number of sites has increased from 6 to 23 over a continuous period of 320 months. So what I'll present today is the evolution of this fishing effort, the CPUE, CPUA, or catch per unit effort, and the revenue, both nominal and adjusted revenue, over the course of that time period. I'll also be comparing it with fish stock assessments that we do with underwater visual assessments. So thank you for paying attention. There's a lot of interesting information in here about sustainable fisheries. I hope you learn a great deal. Thank you very much. The data I'll present here will be based on two of our core activities. One of them is fish catch assessment, essentially weighing fish, putting it in different fish group categories, and weighting it by that, associating it with boats and fishermen, associating it with the revenue, our prices for those fish. And the second part of the work we do is what we call fish stock assessment, or the estimates of biomass of fishable fish in the nearshore environment. I'll bring those two sources of information together because many of the conflicts in fisheries arise because people have one set of data but not the other. And the ability to look at it from both angles of catch, which is production of fisheries, and stocks, which estimates production of fish, is a way to reconcile some of the conflicts that arise in many fisheries where both these sources of data are not collected. The important thing to remember here is that we need to collect certain information, variables that we need to analyze fish catch and stock information. I've listed here some of the key things that are important for estimating. The stock information, which it gives you productivity, requires that you estimate the number of fish, the length of fish, and then use the relationship between length and weight to estimate biomass. You need to do these replicate transects in areas where people are fishing, and you need to break the fish into various fishing groups. We sometimes target, non-target, fishable, and total fishable biomass. You can further break it down into different family groupings or species if you like, if that's important. But mostly we evaluate our data at the community level, that is community biomass. From that, we can estimate production of fisheries, and in our case, that's done through the recovery of fish inside fisheries closures. Kenya has a number of fisheries closures, and we've been estimating biomass in those closures for many years now, and we're able to use that information to estimate productivity in those closures and use that as an estimate of production. So some of those variables are shown underneath that particular stock information. On the right is some of the landed catch information that you need. You need to get weights by taxonomic groupings, and particular price groupings. Also know where this fish comes from, whether it's pelagic or benthic is an important distinction, near or offshore, in the water column or feeding on the bottom. These are important things to know in terms of estimating production. You need to know the number of fishers and the types of gear they use, the number of boats by gear use and fishers. You also need to know the number of fishing days per lunar month and by year, because people do not fish every day of the year, or at least most people don't. And so oftentimes you find people typically fish between 200 and 250 days per year, depending on the location, and that has to be figured out. Cost of fishing is important, such as gear and replacement times. Another thing that's not really captured in most fish catch data is the area from which catch is obtained, and that's extremely important, as I'll show later, in terms of estimating whether a catch is sustainable or not, and what the production is relative to the production potential from the catch stock assessments. Before I go into the details of the patterns in the Kenyan catch, I want to also make it clear that the fisheries analysis is progressing considerably with some of the AI or artificial intelligence methods. This allows us to use data and collect in certain sites and then estimate those same values, whether it's stocks or whatnot, in different sites where you don't have data, using proxies for that data. This would be an example for coral reef fish stocks in the Western Indian Ocean, where we looked at a number of variables. We started with 70, but it turned out in the end about 7 to 8 of them were important, and using that information to estimate stocks throughout the entire Western Indian Ocean. So you can see here that the variables on the upper far left show the importance of those variables. They include things like depth and nation, management systems, water quality issues. Distance from people is an important one. And from those variables, we could predict our actual stock estimates with 85% accuracy with a random machine learning method using training and testing techniques. So this is useful because once we collect data at a certain scale, at certain landing sites, we can then use that information to estimate on larger scales and get a picture of the larger scale issues facing sustainability. So this map here gives you an example of using machine learning to estimate stocks and sustainability throughout the entire Western Indian Ocean. We use about 500 to 600 study sites to estimate the number of things that affect stocks, and then we use that to map the stock biomass in all the 6.25 kilometer squared coral reef cells of the Western Indian Ocean, and that allows us then to use that estimated stock to determine what it is relative to the benchmarks of sustainability, a maximum sustained yield, for example. We can estimate stocks and then what stocks are near or far from maximum sustained yield. And in red you can see the unsustainable or overfished stocks, which are common along the East African coastline and parts of Madagascar. And then you can see areas where the stocks are above maximum sustained yield in these offshore islands of the Seychelles, Mauritius, and the Chagos and Maldives archipelagos. The second important thing you need to know about stocks is their productivity. And we use a holistic approach here for community biomass, or all species combined, to estimate fishable biomass. And here you can see the recovery in all of the Western Indian Ocean closures that we've studied. This is the stock biomass as a function of the number of years since that area was closed to fishing. And you can see in the upper left that in high compliance closures, that it takes about 20 years for stocks to recover to the 100 kilograms per hectare, which we consider sort of the equilibrium biomass. If you use data from low compliance closures, such in the upper right, you'll see that there's more variability, the stocks don't reach the same level, and in some cases there's even a decline in biomass over time. In the bottom left, it also shows that the area of the closure is important for final biomass, that if you don't have areas above 5 or 10 square kilometers, you may also underestimate the final biomass, which is important for estimating recovery rates and times. So here you can see from the model that we use what the stock levels are in the Western Indian Ocean and the countries that we've studied. We include also the Western Indian Ocean and the Central Indian Ocean. That's the British Indian Terrier or the Chagos Islands. You can see there this wilderness area has extremely high stock levels, but as you move into the offshore French territories, Mauritius, Maldives, and eventually down to Tanzania, you see the declining biomass in all of those stocks. And you can see also that when you group those biomass categories together, that most of the Western Indian Ocean has biomass below maximum sustained yield. Seychelles is right on the cusp of that, but by the time you get to Madagascar, Mayotte, Kenya, Reunion, you're now entering into where the nearshore areas are often overexploited, and we can call those areas overfished in terms of their stock biomass. Given that we now have biomass levels and estimated recovery times, we can estimate the time to fish would need to recover to certain levels, for instance, maximum sustained yield with no fishing. So on the left, you're seeing the biomass of stocks in the Western Indian Ocean, very low levels in much of Madagascar and the African coastline, and higher levels in the Seychelles and the offshore islands. And on the right, we can use that information then to estimate recovery time. So areas offshore don't require any time to get to maximum sustained yield because they're above it, but there are many areas in the nearshore areas of the African coastline that will require up to 7 or possibly 8 years of no fishing to recover to maximum sustained yields. So this creates some information about what the challenges are to get recovery to maximum sustained yield. It doesn't mean that people will stop fishing in these areas, but it does give a realistic estimate of the type of reduction and length of time required to get recovery to maximum sustained yield. Now I'll move on and talk more about Kenya's fringing reef, which is the most studied nearshore fishery in this region. We have a long-term time series of studying the dynamics of fishing over time. Prior to talking about the actual fish catch data, I just want to remind you that we recognize that there are different types of fish. Some are fishable, some fish are not fishable, so there's total and fishable biomass. And then you could divide the data, for example, into target biomass. Those are fish that are sellable. People would buy them. They have markets for them, snappers, groupers, emperors, those are good examples of that. And then there's also a category of non-target biomass. A lot of that fish is often taken home or sold on very local markets. In Kenya, it's about a 50-50 split between target and non-target fish. And so if you just measure what's going into the trade economy, it's only about half of what's actually being caught. And that is often going into household food and security and very local consumption. We've measured recovery rates of those fish as a measure of production, and there are differences between them, but the differences are not large, and therefore there's not a big difference that has to be accounted for when looking at productivity of these different fish groups. Another important thing to understand about Kenyan fisheries is there's a strong tidal pattern to fishing. We have a 4-meter tidal range, so neaps and spring tides have very different energy in terms of the tides and also oftentimes the waves. And fishermen have adapted to that over a lunar cycle, since there's a 29 to 30 day cycle, and different types of fishing gear use different days. There are days when people don't fish, such as religious holidays, mostly Friday and Sunday. And then there are times of the tide that people would prefer to be repairing their fishing gear or not. So fishing days does make a difference, and effort changes along those fishing days as does gear. On average, we use 18 days per calendar month, so 10 days are not fished, and much of the data is based on the calendar month. That is, numbers of fishermen per day times the number of days that they fish is often what we call fisher days, and that's often our measure of effort and a useful way to look at fishing because of this lunar cycle in the fishing effort. Based on our studies in the fisheries closures of Kenya, the graph on the left is sort of a schematic but realistic fit to the data of the recovery of fish biomass in tons in Kenya's fringing reef, and we think that a good equilibrium biomass in that seascape is 100 tons per kilometer squared, which means that the maximum sustained yield is about half that level, or about 50 tons per square kilometer. So in many cases, that's our goal, to reach that biomass and get that level of productivity. What we also know is that at that level of biomass that there is a pretty high species diversity. Not all species are there, but a very good percentage, 80-90% of species can be found at that biomass. So it is a trade-off between production and feeding people and protection of biodiversity. So in many cases, when discussing this with fisheries stakeholders, we often use that as a target. And also at that, as you can see on the right, is that we then can estimate what the production of that biomass is, and it's on a daily basis. For the 220 days of fishing, it's 25 kilograms per kilometer squared per day. So that gives you a good idea of what production is like in these fisheries. And when you fish above that level, then you're overfishing, and if you fish below that level, you're allowing recovery of fish. And this gives us a good estimate of what level of fishing we should have. The current biomass, though, is considerably lower than the maximum sustained yield. It's showed in the bottom left. As you can see, the fish there are not really more than a few years old in terms of the biomass, and the yield is also considerably lower than what it could be if fish were allowed to recover. So what we know is that the production now is somewhere around 13 kilograms per kilometer squared under the current biomass, and our biomass goal would be to move to 50, in which case we could increase the yield, double that essentially, and also increase employment of fishermen, probably about double that as well. So we could double the catch and the employment by moving the biomass to 50 tons. However, that's a difficult problem because people have a tendency to overfish in taking fish today, and oftentimes because they don't know what the maximum sustained yield is. But through our efforts, we've been able to calculate that and provide some useful information. So now that you understand that, you can understand the time series and this catch data better. But before you understand that, it's important to understand that many fishermen are making decisions based on markets, that is, the amount of money they'll make in a day, and whether that's sufficient to supply the needs of themselves and the families that in many cases they support. So on the left you'll see the price of fish and that is going up over time, and in the green bar. And then you can see it adjusted for what we call the Consumer Price Index, which is a way of adjusting it for inflation in Kenya. And what you can see there is actually the price of fish is actually slightly lagging the Consumer Price Index, so that although fishermen are getting more money on a daily basis, they're actually losing value of fish based on the cost of living. So the cost of living is something that fishermen think about quite a bit. They're very aware of it, and therefore their decisions are often made whether to enter or exit a fishery based on whether they think they're getting enough income to supply their needs for that day, and that depends on the Consumer Price Index. On the right, you can see the time series of fishing effort in blue, and then the catch per unit effort in orange. And here you get an idea of how things have changed over time. What you can see is during the early part of this time series, there was a rise in catch, a rise in effort until about 2000, and then there's been a steady decline over that time as fishers are exiting this fishery. And I'll explain that a little more in the next few slides. The other interesting thing here was that when effort was at its highest, the catch per unit effort was at its lowest. But as people left the fishery, eventually you find the catch per unit effort returns and comes up. And it's been a fairly narrow window between 2005 and 2022. It's been very close to just a little over 3 kilograms per person per day. And we believe that that window is actually the window in which fishermen feel that it's in their interest or in their economic interest to fish. As long as they can get 3 kilograms per person per day, it makes sense for them to maintain in the fishery. But people enter and exit accordingly, and over the course of this time series, you can see people have largely been exiting this fishery over time, ever since 2000. Consequently, while catch per unit effort has been fairly stable in the last more than 15 years, the catch per unit area has been declining over time. And that's a process of overfishing. If you can see here that people are generally catching more than the maximum sustained yield, and in this case the biomass is below maximum sustained yield levels. Consequently, there's a loss and erosion of catch over time that you can see here. The result is that the revenue on a per area basis is declining when you adjust it for the consumer price index, and that's shown in the light green. The actual revenue is increasing fairly slowly, but if you adjust it for the CPI, you find it's actually declining over time. Consequently, the income from fisheries is declining, as is the yields, largely due to overfishing and the delay between catching productivity and productivity in subsequent years. On the right, you can see it as revenue as Kenya shillings per fisher per day, and also as adjusted by CPI. Also shown are some important thresholds for income. We have the national poverty line in red. We have the minimum wage in light green, and then the national living wage in dark green, adjusted for the CPI. So what you can see there is that while the daily revenue of fishermen has been increasing over time, when you adjust it for the CPI, you find it's declining over time, such that more people are entering into these various levels of poverty. Over time, except for the very early years, very few people were obtaining the national living wage. This is the wage that it requires for you to rely on yourself entirely. It's in the area of about $8 or $9 per person per day. The national minimum wage is more in the area of about $5 per day, and then poverty line is usually around $2 per day. So you can see these changes are unfolding over time, resulting in actually loss of yield, loss of area income, and essentially increased poverty among the fishers that remain in the fishery, despite the fact that the catch per unit effort is fairly constant in the last 15 years. I would like to put some of that cost of living in a more global context, because the patterns observed in Kenya are often common throughout the tropics and even the world. Most recent studies that use snapshots of poverty in fisheries find that most of them impoverished. But in many cases, they're not clear about the causes, and particularly about the effect of the cost of living as drivers of poverty in these tropical fisheries. So what I've just presented here is to remind people what the consumer price index is, benchmarked to 2010 in a variety of different countries. I picked the African coastline, Tanzania, Kenya, Mozambique, Tanzania. You can see there these costs of livings are rising considerably faster than the United Kingdom, the United States, and Japan, and some of the countries like China and in South Africa have more moderate rates of change in terms of the cost of living. So this pervasiveness of cost of living is something to consider when you're thinking about how people can adapt to the ongoing changes in the lost productivity of their fisheries. So here I want to show you how this evolution of effort and catch per unit effort and revenue have changed in Kenya's fringing reefs over time. Here you're looking at some of the earlier data in terms of the CPUE and the nominal daily income. You can see that relative to these thresholds of living wage, poverty line, national minimum wage, revenues, nominal revenues were low, but somewhat above the minimum wage in some cases, but above the poverty line in a number of cases. But through time, you'll begin to see that there is changes that often show a declining effort in terms of the fisher days, which is your x-axis. So as you go through time, people are reducing the amount of effort as they get out in order to sort of keep CPUE and revenue above these particular thresholds. So here we are in 2015. You can see that the nominal wages are going up, but the CPU is more stable and staying within that window. But what's happening is that people are reducing the amount of days that they fish in a year, and therefore they're compensating to keep the revenue within that particular window where they maintain their income and catch in order to avoid the deep poverty and stay within either an early living wage or but this living wage and the minimum wage are also changing over time, as I'll show in a bit. Now let's look at the effort in the catch per unit effort and the catch per unit area over time. You can see here in the early days fishing days were generally above 150 days per month. Fisher days also showing that catches were somewhere near the maximum sustained yield, but often over that maximum sustained yield, such that fish were not being given an opportunity to recover the maximum sustained yield during most of that time. Then as we change time, you can see during the first time there was a peak of fishing effort in 2000, moved things to the right, but most of the time catch was still above that level. But as we move in through time, you can see there's a shift back to the lower fishing effort until finally you can see the actual catch. While the CPUA has stayed constant because of the declining effort, the catch per unit area has declined below the maximum sustained yield, and even though the effort is declining over that period of time. In the end, this is sort of what the pattern looks for all years combined, which is generally a rising catch per unit effort. It's very weak, but it's showing that there's some compensation going on there over time, but the catch per unit area is declining as we go through time and towards lower and lower numbers of fisher days. Now let's look at revenue, both as the nominal, or the price paid at the landing site, and CPUI adjusted. And what you can see is during the early days, people were earning more money when adjusted for the cost of living, even though their actual income was just close to the poverty line during the early years. On the right, you can see revenue on a per area basis, and it shows the same pattern, which is that the revenue was low on a nominal basis, but adjusted for the revenue based on the cost of living was considerably higher. But over time that changes. You get some shift in the right in that peak period of effort, but eventually you start to see the effort starts to decline, and even though the prices are going up and people are raising out of the original poverty line, they're actually declining in terms of poverty relative to the 22 benchmark until finally, eventually, effort is low and the cost of living income is declined despite the nominal price increasing over time. And the patterns are shown here that if you adjust the cost of living, the personal income and the area income is the opposite of the actual nominal price. So it shows the importance of adjusting income for the cost of living. Consequently, to simplify this a bit, I want to talk about the time series in terms of the nominal Kenyan minimum wage. On the left, this is a minimum wage that is adjusted over time, and during the early periods, a large amount of people were above the national minimum wage, but the minimum wage has risen over time, and that's changed the output. On the right, however, I'll show you the minimum wage adjusted for the 2022 cost of living. And again, most people were above that in that period of time, but this changes over time. What you can see is by 2005, people are dropping below the minimum wage. The adjusted wage is not a large difference, but eventually people begin to drop even the adjusted wage over time until about 50% of the people or more are below the adjusted wage, whereas in terms of the minimum wage, nearly all of the people are. In general, you can see that the 74% of the people over that time are below the minimum wage. Just to show another example of this is the nominal living wage, which is the wage you would require to be self-reliant, and it's considerably above the minimum wage, but it's a good estimate of whether people are doing well or not. You can see in the beginning it was sort of a 50-50 split in terms of the nominal and cost of living wage, but over time that rapidly declined until most people are now overall both below the nominal and living wage. In fact, there are essentially no people earning a living wage in Kenya from fishing. So now that I've presented the sort of the problems of fisheries, I want to briefly touch on some of the variability in this data and discuss how that might lead to some improvements and some recommendations. I should say that Kenya is not unusual. Many of these patterns are seen globally. From the literature, we can see not so well resolved data, but indicating very similar patterns. And in Kenya, we have the advantage of having some different management systems in place based on the history of different activities. I'm going to divide Kenya into northern and southern management systems because both of those are counties and systems that have followed slightly different management system. In particular, I'm going to talk about the northern system as a system of marine protected areas. We have the Mombasa Park, the Wambatama and Lindi Park in the north, and people have embraced these community closures. We have 3 of them that largely seem to work in getting some recovery of fish biomass. And the northern part has not taken so many of the subsidies that are being given to fishermen often through World Bank loans to Kenya. The southern management system had an attempt to have a marine reserve, but it largely failed, and it was replaced by gear restrictions on pull seines, and that's led to a temporary rise in catch per unit effort in that area, but eventually a decline that I showed earlier. And the county and the national government have been subsidizing boats, freezers, and gill nets in that area. So we have 2 cases where there is subsidies, but in the north it tends to subsidize protection more, and in the south it tends to subsidize extraction or reduce the cost of fishing. So the question becomes, what are the rates of change like in these 2 systems, the north and the south? Is the area with subsidies protecting doing better than subsidies that extract? And the general answer is yes, but it depends on what you look at. In the upper graphs you can see the rate of change relative to the actual mean value of, in this case, fisher days per kilometer squared per month, and the higher the fisher days are, the faster the decline in fishing effort. So that occurs in most of the sites, both in the north and the south. There's a few in the north that seem to be not declining, but in general there's a decline. Statistically, however, there's not a significant difference in the slopes of those 2 different management systems. However, when you look at the yield, there are differences. Although there are many negative slopes, if you look at the mean difference you'll see that the rate of decline of catch per kilometer squared per year is actually declining slower in the north than it is in the south. So it would suggest these subsidies of protection are actually causing a slower rate of decline than we are seeing in the southern sites. Revenue is an interesting case here where we're seeing both nominal in the top and adjusted revenue in the bottom. Interesting that nominal revenue is rising, as we've shown before, and that there are differences with the south coast declining faster than the north coast, but the differences are not particularly large and there's a great deal of scatter. However, when you adjust the revenue for the cost of living, you can see much larger differences with the north maintaining a slower negative decline in revenue than those people in the south. So relative to the adjusted rates of cost of living, the areas without protection subsidies are doing poorer than those with protection subsidies. Consequently, the subsidies are essentially making people poorer. One of the things I was interested in, what were the consequences of these losses of catch and revenue over larger areas of the Kenyan coastline. You can see here I've made an effort to calculate the estimated loss for the north coast, which is around 200 square kilometers, versus the south coast, which is 100 square kilometers. And what you can see is the loss rate in the north coast is around 4 kilograms per kilometer squared per year, whereas in the south coast it's 117 kilograms per kilometer squared per year. So if you look at the cumulative loss over the course of this period of time, you're getting as much as 300 tons being lost on the south coast and a much smaller amount, less than 25 tons, being lost in the north coast relative to the starting date. If you look at revenue, the revenue loss is smaller in the north coast than in the south coast, but the north coast is twice the area, so the revenue loss actually is compensated by the area being larger in the south than the north coast. Anyways, are these large losses? Well, relative to the total catch in Kenya, these are not particularly large losses, but they are important sources of food and nutrition for many of the people on these reefs. And we're really not sure how this pattern would be seen if we did similar analysis on the larger scale of Kenya and in fact on the Indian Ocean in total. But we can expect there are continuing losses, and much of it depends on the management systems in place in these different reef systems. So these fisheries in southern Kenya have been very insightful into improving analysis of fisheries. That is, we've developed a holistic picture of production, and to do that we had to both have catch and stock evaluations there in their reconciliation. We are able to reconcile these two sources of information, and that they now make sense as when they're coupled rather than independently. This catch itself would not really tell us whether we were overfishing or not unless you put the catch on a per area basis. But the catch per unit effort is not really useful in terms of evaluating fisheries, and yet that is the most common way of evaluating fisheries. Consequently, there is a global problem and over-reliance on catch per unit effort because area from which fisheries are caught are seldom evaluated. We've seen that fishing effort has been declining due to an overshoot in 2000, and that's caused an exodus of fishers and lost employment over time. So while the number of fishermen people claiming to be fishermen may be stable to rising, the reality is they're not fishing as many days, and so they're losing employment by this equilibrium force that is causing them to not make the money they need, particularly when you consider the income needs on an adjusted basis, accounting for the cost of living. Resource extraction subsidies are actually hastening the decline, so despite the perception that these subsidies will restore the fishery, there's no evidence for that, and here it's quite quantitative that we can see that extraction subsidies actually exacerbate the problem, and yet that's the common management system in most of the world today. Resource protection subsidies are slowing the decline, and they could possibly contribute to increases, but they'd have to be part of larger efforts to balance effort and production, which is a major stumbling block for most fisheries. One of the nice things about this combination and the modeling aspects of it is that we can come up with very specific recommendations based on the amount of effort we believe are appropriate, the amount of stocks that we think are appropriate, the amount of yields that are appropriate, the amount of effort to get those stocks, and also in terms of what it takes to keep people above the poverty line, the minimum wage line, and the living wage lines in all these systems. So these are our estimates here. I won't go through them one by one, but we can at least come up with goals and guidelines. These may prove to need refinement in the future, but they are pretty useful now for taking us out of this mysterious area of understanding fisheries yields, catch per unit effort, catch per unit area, revenue, adjusted revenue, and giving us some quantitative suggestions for getting people out of poverty and developing some of the national goals of poverty reduction that account for this rising cost of living in Kenya and many other places in the world. So before I conclude, I wanted to give some examples of the spatial variability in fisheries production, because not all of the world is like Kenya's fringing reef. There are different types of nearshore systems in the tropics. A very unique, common differences between fringing reefs and what we call island reefs. These are isolated islands with reefs around them, and they may have different production and management needs because of the differences in these geographies. So in East Africa, we have these two types of systems. We have the Kenya Southern fringing reef, and then if you go to southern Kenya, south in Tanzania, the islands behind the big islands of Zanzibar and Pemba and Mafia, there's a series of coral reef islands in this back reef area. And one of the questions I wanted to ask myself is whether these two systems, which are common throughout the tropics, might require slightly different estimates of production in order to not generalize too much about the conclusions just from the Kenyan fringing reef. So I'll conclude with some effort to show you how variable things are in these two different systems. These are these two geographies. On the left is Kenyan fringing reef that I've talked about, and the right is the Tanzanian system. And within those systems, we've been measuring fish catch in the north, but we've also been doing stock assessments throughout these island reefs. And we've also been looking at recovery inside fisheries closures within these systems. So we do have a pretty good understanding. May not be quite the same level of detail as in the fringing reefs, but there's enough understanding to be able to make some pretty fair comparisons between the two. This graph would be an example of the kind of differences. This is the recovery of fish in island reefs and fringing reefs, and you can see there are differences. In general, fringing reefs have slower recovery rates, so lower levels of productivity of fish than the fringing reef, but they also tend to equilibrate at probably considerably higher levels of fish biomass. It may be that these islands are more aggregating areas where fish aggregate and then feed out from it, but it takes a longer time for them to recover, possibly due to lower exposure to ocean environments, a more lagoonal type environment, and therefore lower productivity. The result is that you would need different models of production, and that may influence your estimates of maximum sustained yield and your estimates of the productivity potential in these two different systems. So the recovery and the productivity and the biomass are shown in these slides. We have the recovery of biomass on the left and the productivity estimates on the right for fringing reefs in red and island reefs in green. And you can see there are differences in the levels of recovery in terms of the final equilibrium biomasses, but also the recovery rates and the estimated productivity as a result of that. As an example, island reefs have higher final biomass than fringing reefs, but the productivity is lower, as shown on the right, and the peak productivity occurs at a higher biomass than fringing reefs, so at 80 tons per kilometer squared per year rather than 50 tons per kilometer squared per year in fringing reefs. Another interesting thing is that the current biomass is actually lower in fringing reefs than island reefs, despite the higher productivity, and it may be that the higher productivity allows fishers to reduce that biomass to lower levels and still get the productivity they need to make minimum incomes. But the result too is differences that affect the recovery rate as well. But even though there is lower biomass in fringing reefs under the current levels of fishing, the productivity is higher, so that if they do stop fishing, the time to recover to maximum sustained yield is estimated at 8.6 years, whereas in the island reefs it's estimated at 11 years. So these are considerable periods of time to have no fishing to recover the additional productivity and potential yield out of these systems. So the question is, how generalizable are these two systems to the Western Indian Ocean? Well, of course, there's going to be variation with latitude and other things, exposure to the open ocean, etc. But I believe these are probably two good cases, maybe possibly at the outer extremes. Fringing reefs being exposed to open ocean are going to have high productivity, and lagoonal systems in leeward areas behind islands are going to have less exposure to the ocean and lower productivity. So these may be sort of the upper and lower confidence intervals for coral reefs on larger scales, but more research is going to be needed to determine if in fact that's the case. From the difference in production between island and fringing reefs, you can also model the fishing effort that can be sustained under maximum sustained yield and under current biomass, and you can see the differences in the fringing in the top and the island and the reef, that the fringing can contain more productivity and therefore contain more effort at maximum sustained yield and current biomass. But in many cases, most of that production, it takes very few fishermen to get people living wages in most of those systems, often lower than 2 or 3 fishermen per square kilometer. The island reef is more challenging because of the lower production, and you're talking numbers that are considerably lower, often less than 2 or 1 fisherman per square kilometer in order to get living wages in that particular system, depending on if you're harvesting for maximum sustained yield or you're harvesting under the current reduced biomass. Here we look at rates of change of each of these landing sites over a period of about 3 years to see whether they also show the patterns we saw in the fringing reef, and in general they do. What they do suggest is that the island reefs are closer to a sustainable effort and CPU and CPU catch per unit area, because some of the sites lie above and some lie below the actual zero equilibrium, whereas in the case of fringing reefs, in the case of effort and catch per unit area, most of the sites lie below this 0 point of no change. So there are interesting differences, but one of the patterns as well is that both of them have positive income due to the rising prices in both locations. But if you adjust that again for the cost of living, those positive values actually decline over time. This is not a large data set in the sense that these are 5 to 6 sites sampled over a shorter period of time, 3 to 4 years, but they do indicate very similar patterns to the fringing reefs, and some differences that are insightful in comparing fringing and island reefs. So this interesting comparative approach has allowed us to make very specific recommendations, again, based on estimates of production. The island reefs are expected to have lower production, around 4.1 tons per kilometer square per year, whereas fringing reefs are closer to 5.6, and this translates into different daily rates of 13 and 25 kilograms per kilometer squared per reef. And yet, under the current biomass, you cannot reach those particular levels. It's as low as 11 under the current biomass in fringing reefs and more around 5 kilograms per kilometer squared in the island reefs. So even though there's lower production in the island reef, it's actually the fringing reef that's showing more overfishing effects than we're seeing in the island reefs. And that may have something to do with population density, the nearness to shore, and other things that affect fishing effort. We can have current goals and goals at maximum sustained yield, and these will allow different levels of effort and have implications for catch per unit effort, catch per area, and revenues, particularly as adjusted revenues. Consequently, these studies that compare sites there needs to be more of these to see if these are typical. We expect these are kind of typically within the range, but we expect these things to change with latitude and exposure to the open ocean. May be different in windward versus leeward, Madagascar. All of these things are expected to have some effects, and we hope that in the course of the evolution of the science over the coming decades that more of these variation will be exposed, and we recommend people consider our methods carefully. They've been tuned over many years of work, and they seem to be converging on understanding these systems much better than they were some decades before. Well, thank you very much for paying attention. I hope you learned a lot about coral reef fisheries and sustainability. I've learned a great deal over the last few decades, figuring out many of these interesting patterns. This work was done through collaborations with many people, as you might imagine. Some of the people have come and gone and retired and other things, but it couldn't have been done without the inputs of a large number of people. I'll mention a few of the funding organizations. That would be Tiffany, Bloomberg, MacArthur, USAID, and WIOMSA were among the donors of various parts of this work in different periods of time. We've always had some very good collaborators in Kenya. That's been the Kenya Wildlife Services. That has allowed us to work inside the parks. We've worked closely with the Kenya Marine and Fisheries Research Institute through various collaborations with many of the employees there. We've worked with Kenya's Fisheries Department in measuring the fish catches. And in Tanzania, our main collaborator there has been the University of Dar es Salaam and the Institute of Marine Science, where we've worked with a number of students and faculty in that department. We're very grateful for all these collaborators. I'm particularly grateful to the fisheries communities that we work with that have allowed us to measure fish catch in all of these landing sites. They've been very keen to see what we find out, and they attend annual forums where I present this information to them in Swahili, in their local language. And I believe they've learned a great deal. They've taught me a great deal. In many cases, they point out some issues that concern them that I'm not always aware of. And I'm very grateful for that kind of review that we have going between communities and the fisheries. It's been a wonderful experience for me, and I hope we can pass on this interesting case studies to make more effects, bigger and better effects in achieving sustainable and biodiversity needs for tropical coral reefs. Thank you very much again.